I am just sending out the link on Remind. So if it sounds like I'm typing away, it's okay. Chemistry, atomic structure, live review. Tune in now or later. All right, so I'm going to get started pretty quickly once this sends out. Maybe. Send. Being weird. All right, I'll get started in a minute. I'm just trying to send the link out on my Remind. And it looks like it's just not working. Looks like all of Chrome. Well, I'm going to double check that it's sent out. Just trying to get my students the link. So if you're watching, just give me... Remind just kind of crashed on me. So... Oh, Remind might be going under maintenance. Nope, it's working. All right, it went through. Okay. So we're doing atomic structure today. So protons, neutrons, electrons, the history of the atom. That's a big one. And all that stuff. So let me get my outline out, and then we'll get going. All right. I guess let's just start straight up with the history. Who are the people? There's like very few people you actually need to know for the Chem Regents. So let's start off with that. So we'll start with the history of the atom. Person of interest, number 1. The first one is Dalton. Dalton's kind of like the father of atomic theory. He was one of the first ones to postulate that atoms exist. And he had like the cannonball theory. He thought atoms were these hard spheres, like a cannonball or like a billiard ball, like a pool ball. And he didn't really know anything about the subatomic particles. But he just kind of proposed that atoms exist. And he didn't really have any theories on the protons, neutrons, and electrons. He didn't really know too much about them or if they were around. But he was like, there's these things, they're really small, they're smaller than cells. I'm going to call them atoms, and they're kind of like hard spheres. Next guy, his name was J.J. Thomson. And there's a few buzzwords when we think of Thomson. He used this thing called a cathode ray tube, which actually used to be in your TVs way back when, but that's besides the point. And he used this tube, and he noticed that it was like deflected by the negative electrode toward a positive electrode, and so he essentially discovered the electron. So that there were these small negatively charged particles somewhere inside the atom, but he didn't have a great idea of what the atom looked like. So he knew these negatively charged particles were somewhere. So he developed what he called the plum pudding model, but kids don't know what plum pudding is. I don't really even know what plum pudding is. So I like to think of it as the chocolate chip model. So he kind of thought the atom was like circular, and that these electrons were like chocolate chips in a chocolate chip cookie. And they were just kind of around, but he didn't really have any ideas about anything else. He was just like, there's the electrons, and they, you know, exist, and they're just chilling, floating around in this thing that he called plum pudding. And we're there, to me, they're more of the chocolate chips to your chocolate chip cookie. And plus, cookies are delicious, so I like to think about cookies. And that's about it. So he was big on the electron. Rutherford was next. Good old Rutherford. Not Rutherford B. Hayes, great president. Another Rutherford. He did the gold foil experiment. That was his deal. O's and I's don't go together. The gold foil experiment. That was him. I can spell. And he just basically bombarded gold foil with these alpha particles. So he took this gold foil, that's gold foil, and he fired these alpha particles at it. And most of them, as they were going through, just passed through the foil. But every once in a while, they would hit something and bounce away. And the rest of them would just kind of pass through, and then they would hit something and then bounce away. So his gold foil experiment discovered a few things. Atoms are empty, mostly empty. And there is this dense, and he knew it was positively charged nucleus. So he was the main guy that knew there was a nucleus, knew atoms were mostly empty, but in the middle, there was this really dense, positively charged nucleus. And he didn't propose protons, but these positively charged particles in the nucleus, those are protons. But he didn't propose the idea of a proton. He just knew there was stuff in the nucleus, and it was positive, but he didn't call them anything. And that was about it. Next up is Bohr. He's the one most people are familiar with. Maybe not his name, but at least what his model looks like. He was the planet model, where the electrons orbit the nucleus. So his model kind of looked like this. So you have the nucleus in the middle, and that's positively charged because that's where the protons are. And the electrons just kind of orbited around the nucleus like this. And these are all negatively charged. So we got a positive nucleus with a bunch of negative electrons just kind of swarming around it like planets orbiting the sun or any other star, depending, it doesn't have to be our solar system. So he proposed this idea. He also proposed the idea of excited state and ground state. So he said that these electrons can move from one energy level to another. So these electrons here in this lovely looking picture of mine, I'm very artistic. I should probably become an artist. These electrons here can move up and down. And he called that going from the excited state to the ground state. So when they absorb energy, when the electrons absorb energy, they go from ground to the excited state. These are not the same as ions. I'm going to make sure to cover that again later. All right? So, not the same as ions. I'll cover that more later. So, when they absorb energy, they go from the ground state to the excited state. This is not very stable. They don't stay here forever. When they emit energy, they will go from the excited state back down to the ground, and when they do that, they will release some form of light. So when they absorb energy, so if you input energy into the atom, it hits an electron, it'll absorb that energy, let's say heat, it'll absorb that energy and move up to an excited state. Once it falls back down to the ground state, it will emit the same amount of energy it absorbed, and it will release that energy in the form of light. And we did this in class with the spectrophotometers. So we showed this using atoms that emit this energy using visible light. It doesn't have to be visible light. Some atoms, when they go from excited to ground, will emit infrared or UV or something on the electromagnetic spectrum. But we like to use examples in class that emit visible light because you can see visible light. So electrons will absorb energy to go to the excited state. When they fall back down to the ground state, they will emit that energy in the form of light. And that's what Bohr had to say. That's what Bohr had to say. And then the last model, which I always kind of attribute to Schrodinger, but the Regents will call it the wave mechanical / cloud model. And basically what you need to know about this is the word orbital. And I know you hate this already because you see the word Bohr and you hear electrons orbit the nucleus. And then when you go down to this model, all of a sudden electrons are in orbitals. Is that the same word? Not the same word. Not the same. Similar. Looks similar. Not the same word. This is the probability. So this model said you never really know the location and momentum of an electron. You can only know one or the other at any given moment. So we say these electrons exist in orbitals. There's a bunch of different kinds of orbitals. In some of the classes we covered this, SP, DF. Those are examples of orbitals. Don't worry about SP and DF for the Regents. But this is the probability of finding an electron. So we can't say for certain, oh, the electron's right here, and it's just orbiting the nucleus right there, and I know where it is. You don't know where it is, because if you try to see an electron, let's say this is the nucleus, the electrons just kind of exist like a cloud around the nucleus. So you never actually really see them. So they're just kind of like a cloud, kind of like this. All right, so you never really can say where they are at any given moment. They're just constantly, it's almost like they're everywhere, but nowhere. No, so they look like it's like a cloud. It's just like a blurred, jumbled mess of where electrons could be. So we would say this is an orbital where the probability of finding an electron at this energy level is somewhere in that region. And that's called an orbital. So that's the history. You need to know these guys, unfortunately. But they're literally, maybe other than Arrhenius, I can't think of any other person's name that really comes up in all of chemistry. Some teachers, when you did the gas laws, might talk about Boyle's law and Charles' law and all those people. But knowing their names is not important for the Regents. It's nice to know. It's not the historical aspect of all this, but you don't need to know Boyle's laws. P1V1 equals P2V2. So, Dalton, atoms are hard spheres. That's about it. Thomson, cathode ray tube, discovered electrons, said there were these small negatively charged particles. Plum pudding, which I'm going to say is a chocolate chip cookie. Rutherford did a gold foil experiment, fired a bunch of alpha particles. Most of them passed through the gold foil. Some of them didn't. So he knows that the atom is mostly empty because most of them just went straight on through. But some of them deflected back. So there's something in the middle that's dense and really positively charged. He called it a nucleus. He didn't discover protons. He didn't name these protons, but those positively charged particles in the nucleus are protons. Bohr, planet model. Electrons orbit the nucleus like a planet orbits the sun. He said that these electrons can move on these energy levels we see here. So they can move up and down to orbits that are further away. If they absorb energy, they're going from the ground state to the excited state. If they release energy, they go from the excited state back to the ground state, and they will release this energy in the form of light. Sorry. And then the wave mechanical model / cloud model said electrons exist in this probability region that we call an orbital. So speaking of subatomic particles, what are they? And what do we need to know about them? So what are the things that make up atoms? There's more things that make up atoms than these three. There's even smaller things than these three. But these are the three need to know. So we have protons. They're in the nucleus. They have a +1 charge. And they have a mass of 1 AMU, which is atomic mass unit, which is also sometimes abbreviated as just U. The symbol for a proton will sometimes, you'll see it like this, 1, 1, P. P for proton. That top left number is the mass. That bottom left number is, you can think of it as. So it's got a +1 charge and a mass of 1. The the neutrons, they are also in the nucleus. They have no charge, but they have a mass of 1 atomic mass unit. Again, sometimes abbreviated as just U. So their symbol would be an N with a mass of 1 and a charge of 0, because they have no charge. Electrons, we've already talked a lot about. They are on the outside of the nucleus. They have no mass, but have a -1 charge. So the electron, sorry, no mass. Come on, Mr. G. No mass, but have a charge of -1. And we symbolize them using the letter E. Electrons technically do have a mass, but it's so tiny we just assume it's 0. All right, how do we calculate protons, neutrons, and electrons? Protons are the same as the atomic number. So when you look at the periodic table of elements, not the other periodic table. When you look at the periodic table of elements, here's all my notes from last time. What was I talking about? It looks like periodic trends. All right, so let's zoom in. I'm going to zoom in onto this key right here. So the periodic table, believe it or not, has a key that shows you what every single one of these numbers mean that you're looking at. The atomic number here is the protons. That's your protons. I'm going to run out of room. That's okay. Those are your protons. So when you are looking at any given element, you'll notice the whole periodic table is organized by atomic number. It goes from 1, ascends down and to the right until you get to 118. But the atomic number is unique to each element. If you change the atomic number, you change the element. Guarantee. All right, so that is where you can find out how many protons are in a given element. All right, let's go back. So let's say calculate protons. How do you calculate neutrons? Neutrons. You take the mass number minus the atomic number. So let me clarify a couple things here. The mass number is not the same as the mass on the periodic table. This is the atomic mass on the periodic table. And it's always a decimal because this is a weighted average. And I'll go over a weighted average of what it is later. But this is a weighted average of all the naturally occurring isotopes for whatever element we're talking about. The mass number is just the protons plus the neutrons of any given atom. Carbon 14. what are the protons and neutrons in carbon-14. So for example, you can show this two ways. You can say if we're doing carbon-14, C-14, that's the mass. So to get the neutrons, you go to the periodic table, look up carbon's atomic number. Its atomic number is 6, which equals the protons. Then take its mass number, 14, minus 6, mass number minus atomic number, and you'll get 8, which is the neutrons. So that's one way they'll express mass number to you. The second way they can express mass number is like this. Almost like how it looks like on the periodic table with the mass on the top left and the atomic number on the bottom left, but it won't be a decimal. So here is your mass number. Here is your atomic number. Subtract those two, and again, you'll get 8, which equals neutrons. Electrons. How do you figure out electrons? The electrons will equal the protons if neutral atom. So atoms, by definition, are neutral. Electrons will be different. Electrons will, I know how I want to say this. Let me erase that. Electrons will not equal protons if charged ion. So if it has a charge, the electrons and the protons are not the same. If it's just a neutral atom, like it says atom, it has an oxidation state of 0, there is no charge, the protons equal the electrons. So for these two carbons here, there's no charge given, so we would just say that this carbon atom has 6 electrons because they're neutral. If a charge is given, sometimes they might give you a charge. Let's say we're doing magnesium. It weighs 12. I'm going to give it a mass number of 25. I'm going to give it its charge on the periodic table, which is +2. To figure out how many electrons this has, let's do all of them. Protons equals the atomic number, which is 12. Neutrons equals the mass number, which is 25, minus the atomic number, which is 12, and you get 13. The electrons will equal the atomic minus its charge, which in this case will be 12 minus 2, which is 10. And that's correct. So this has 10 electrons. Mr. J, I have a question. What if the charge is negative? That's a great question. If you have oxygen, come here. That should be an 8. 8. Protons equals 8. Neutrons will equal 17 minus 8, which would be 9. Electrons will equal 8 minus its charge of -2, which in this case, that double negative turns it into 10, which is true. So the key thing to keep in mind is since electrons are negatively charged, they're negatively charged. When you gain electrons, you equal negative. You will have a negative charge. When you gain electrons, if your electrons, which are negative, are greater than your protons, which are positive, then you're going to be negative. If your electrons, which are negative, are less than your protons, which are positive, then your overall charge will be positive. It's a little counterintuitive because you're like, but I'm gaining things. I know. But you're gaining negatives, so you become negative. Subatomic particles. let me kind of reiterate the difference between atoms going from, or electrons going from excited to ground state and vice versa, and an ion. So, when you go to the periodic table, in the bottom left corner, you will see these numbers, 2-4, 2-8-4, 2-8-18-4, okay? That, if we look at our key, look at the key, the reference table is here for your help, here to help you. If you look at the electron configuration, what does that mean? What does this mean this has an electron configuration of 2-4? So I'm going to do, let me pick another one. I don't want to do carbon. I'm going to do chlorine. Let's do chlorine. Chlorine's electron configuration is 2-8-7. Everything on the periodic table is in the ground state. Meaning that here's our nucleus. There's 2 electrons here. 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second energy level. And then 7 electrons in the third energy level. So when you see all of these electron configurations on the periodic table, again, I'll rewrite chlorine here. This means this is the first energy level, second energy level, third energy level, or shell. Other words they will use. So there's energy level or shell. So you can think of these as energy levels or shells going across. This is the ground state. Chlorine's electrons naturally exist. Now, if chlorine were to gain energy in some way, I'm just going to erase this so I have room. If chlorine were to gain energy in some way, it could turn into a variety of excited states. And all this means is that the number of electrons you see here will stay the same. So you have 17 electrons in chlorine. They're going to stay 17. But when they get excited, they move from a lower shell or a lower energy level to a higher energy level. And there's any combination to do this. You can take 1 away from the 2 and bring it up to the 8. You can have, sorry, I already messed up that. If you take it away from the 2, that 2 becomes a 1. The 8 gains an electron to become a 9, and the 7 remain the same. That's excited. Or 1 could go from the 2 to the 7, and it becomes 1-8-8. Or the only other possibility for chlorine, again, to become excited, it needs to jump up an energy level, is to go from the 8 to the 7. 2-7-8. So these are all excited. All that means is that the electrons are in higher energy levels than they were before. But the amount of electrons stays the same. When you have an ion, that means you have either gain or lose electrons. So the number of electrons will now change. So if we take chlorine again at 2-8-7, if you look at chlorine's most popular charge, the top charge of chlorine, it has a charge of -1. And we know from before, if we get chlorine's atomic number of 17, when you do 17 minus -1, you will gain electrons. So chlorine has gained an electron. So when it becomes an ion, its electron configuration changes to 2-8-8. This is not excited. This is an ion. So, ground state to excited state, when you go this direction, the electrons will stay the same. When you become an ion, your electrons will increase or decrease. An anion kind of sounds like the word onion. Onions make you cry. They're negative. Onions are just kind of negative people. But they're not people. But if we pretended they were people, they'd be negative, and they make you cry. If we look at something like magnesium from before, charge +2 with its 12 protons, 12 minus 2 would be 10 electrons. This is a cation because it's positively charged. And we can figure that one out because that T kind of looks like a plus sign. I am not making any sort of analogy with a cat. I hate cats. So, the plus sign. If you like cats, sure, you might remember it. But I think you should just look at the plus sign. Okay, so we just talked a lot about ions. Now I want to go to the other term involving changes in subatomic particles called an isotope. So an ion, protons are the same. You never really change the protons. If you change the protons, you're a totally new element and you've totally changed everything. Your neutrons are the same, but your electrons are going either up or down, depending on if you're a positive ion or a negative ion. But an isotope is a little different. Your protons are the same. Neutrons now will go up or down. Usually they change going up, but they can change. And your electrons will stay the same. So, what this means, the isotope will change the mass. Change the mass number. Versus your ion changes the charge. All right, so when you see the word isotope, you think protons are the same, but the neutrons are different. So I'm going to write a few different I'm not going to write isotopes. I'm going to write a bunch of atoms here. I want you to spot the isotope. So we have Na1123, Na1223, Na1124. Let me give you some more space here. So this was Na1223 or Na1124. So, now let me do more. Na2412. Isotopes. Protons are the same. Neutrons go up or down. They change in some way. First, I need to check what Na's atomic number is. Na's atomic number is 11. So the isotope needs to keep this number the same. That 11 cannot change, or you don't have an isotope, you have a totally new element. So, this is normal Na. Let's say. I am designating that as the normal one. An isotope of this can't be that one because 12 protons is magnesium. The mass here also stayed the same, so that's doubly wrong. Here, the mass is different, which is good. If the mass changes, the neutrons change. But the atomic number changed as well. That would be your isotope. All right, so that's a basic introduction to isotopes. Now let's do the fun part of isotopes. One of the few, if not the only thing that I can think of right now that involves a bit of math that's not given to you on your reference table. Let's go back here. So, these atomic masses are decimals because they are the weighted average of all the naturally occurring isotopes. So these are the weighted average of natural isotopes. which means, uh-oh, you gotta calculate these. So let's do an example. How do you calculate the weighted average for an isotope of any element? I'm going to do chlorine again. Chlorine has two naturally occurring isotopes. There's chlorine-37 and chlorine-35, where the one that weighs 35, its mass is about 34.96, let's just say. And that percent is 67. And then the other one has a mass of about 36.96, and that has a mass percent of about 33. You need to tell me what the weighted average is of these isotopes. Now, some of you might be like, whoa, Mr. G, can't I just look this up on the periodic table and I don't have to do any work? 9 times out of 10, there's 2 questions they're going to give you. The first one is, they'll give you an element X that doesn't exist on the periodic table, so you have to show your work anyway. And then the second thing they'll say is, show the numerical setup for solving this problem. So you have to do it either way. I'm going to go over what I think is the easiest way to do this. Take the mass of the given isotope and multiply it by its percent given. Then you need to add that with the percent and the other mass multiplied together. Then when you add those together, at the very end, divide by 100. So if the question asks you to show a numerical setup, this would be good. That's set up. Don't solve anything. Because as soon as you start solving, we need to grade you, and we need to check that what you just did was correct. And you might goof. So don't goof when all you have to do is just kind of, that's it, move on. Turn the page, go to the next question. Don't do any more work than you have to do. 1-point questions deserve 1-point answers. All right, let me do another one. I know usually I said I wasn't going to do examples with these, but a lot of these types of questions you need to see just like what I'm talking about. So, boron 10 and boron 11, mass and percent. Actually, I'm going to make up another one. No, this is good enough. So, mass of this one's about 10.01, and its percent is about 20. In this one, its mass is about 11.00. Nope, that's 11.01. Eraser. Thank you. And its one's percent is going to be about 80. So, multiply the first two, plus multiply the second two, divide by 100. Boom, done. Done. So, that's all you have to do. Don't go crazy. Let me see. What else do we got here? I don't want to do dot diagrams tonight. We did ground state versus excited state. Bright line spectrum. Oh, God. I should have copied an image. Now I have to draw this. I didn't want to do that. That's okay. Let me piggyback to electron configurations again, which will piggyback to excited to ground state, which will then go over the emission spectra. And then we'll call it a night. Woo! Dunzo! Love it. Okay, so electron configurations. So let's say you had... let's look at the periodic table. first, I'm going to cover this more in the periodic table video, but any group, the groups as you go down, are all chemically similar because they all end, their electron configurations all end in the same number. So if we take sulfur, sulfur's 286. This 6 is called the valence shell, meaning these are the valence electrons. These are your bonding electrons. These are used most often in bonding. Okay? So when you look at the ground state for any atom, those last electrons are called your valence electrons. And I think I just wanted to point that out. Just like, hey, by the way, don't forget this. Because I'm going to draw these dot structures another day. But I just want to point that out. Those are called valence electrons. And we also know when you're in the ground state for sulfur, these electrons can move from a lower to higher energy level. So, for example, they can do this. And this becomes 2-7-7. Excited. But they don't stay there very long. When this electron moves back, and you go back to the ground state, ground, I can't write, Mr. G, what is wrong with you? When they go back to the ground state, they release that energy. So this step right here will release energy. This step right here absorbs energy. This constant moving of electrons from excited to ground state will give off a unique spectra for that element. So each atom, or element, if you want to think of it that way, has unique spectra. Each one, actually, I wonder if I have one of these, has a unique spectra. And what I mean by that is when these go from excited to ground state, please be in this. This would be a lifesaver. When they go from excited to ground state, you will see a certain spectra of light. Yes! Oh, so great. And it looks like this. So at any given wavelength, these spectral lines represent that excited to ground state transition. And each one's unique. So each element has their own unique spectra. They like to give questions where they show you a bunch of elements and then show you a mixture, and you have to identify which ones are in the mixture or which ones are not in the mixture. It's like every single Regents pretty much has a question like this. And all you have to do is follow the lines from the element to the mixture and see which ones line up and see which ones don't. And if there's even one line that the element has and the mixture doesn't, it's not in the mixture. So, let's start with D. Red. Oh, there's one. There's that one. Hey there. Love it. Look at you. Boom. Okay, so D, check. D's in the mixture. Different color. Let's do E. Whoa, would you look at that? There's that one. Check. Check. E, check. In the mixture. But G, poor G. Poor Mr. G, really. G? No, that's not there. That's not. I mean, you can stop right there. As soon as you find there's one that's not in the mixture, G, nope. Sorry. So only D and E are in the mixture. Atomic structure. I think that's where I want to end it. I feel good. I don't know how you feel. There's a similar question, Bright Line Spectra. Ooh. I will try to post this video tomorrow. My video from yesterday came out all goofed. I don't know what's wrong with them, but they keep coming out like the first 20 to 30 minutes is perfectly fine. And then all of a sudden it just speeds up really fast and does the last half hour in 2 minutes. So I have all the practice problems ready to go. If you're itching to do those, don't worry about it. I will get this video and I will get the practice problems up on my website hopefully tomorrow. If not, I will at least get the practice problems up because I don't have to worry about YouTube for that. Thank you again for tuning in if you're watching. If not, these videos are on my teacher site anyway. And that's it. That's all I got. Good night.